Hello, this is Wolfgang, and today we're going to talk about censorship resistance in Ethereum and inclusion lists. Recently, I've been reading a lot about inclusion lists, and I think it's a very interesting topic, and it's touching on one of the most important points and value proposition of Ethereum, that is censorship resistance. So I'm happy to talk about it more in detail in this video, and see how Ethereum researchers are proposing changes to the protocol such that we can have better censorship resistance. So let's start from the beginning, and why even talking about censorship resistance? Well, this is really one of the most important values of Ethereum, I would say, when we talk about Ethereum being decentralized and the fact that you have the possibility to have a lot of or a long tail end of full nodes. This is not for fun. It's not just a hobby or just you want to solve a difficult problem. You don't want to achieve decentralization just for decentralization, but what you care about are the effects of this decentralization. So if you have this big set of full nodes, validating full nodes, you want to use them. I mean, what is the effect? What is the value of it? And a value of it would be censorship resistance, because you can assume that a part of these tail-end full nodes or validating full nodes will be honest and will not censor transactions. And this is one of the value proposition of Ethereum. We want to build like an open, permissionless network where anyone can access the resources of the network by paying a fee, of course. But still, nobody should be censored just because there is a central authority that believes that this transaction cannot be part of Ethereum. If you have that, then you're not decentralized. And if you have that, despite having 1,000 solo stakers that are validating the network and still the network is censored, then what's the point? So censorship resistance is important, and we should all agree on that if we care about Ethereum. So how do you quantify censorship resistance? Like, how do you know if you have enough censorship resistance or not? The point here is to make it very costly for a censoring builder, for a builder, to exclude a transaction from a block. Let's say that there is a transaction and the builder doesn't like it, doesn't want to have it included in a block. We cannot really force the builder to include it, or maybe we can, we'll see. But today we can't. But at least we can make it very costly. So if the builder wants to exclude the transaction, he can, but he has to pay a price. And very costly, up to a point that at some point it's impossible. That's how you get censorship resistance. And yes, this is a problem. This is a real problem. It's just not theoretical. You can check the state of censorship in Ethereum. This is specifically for OFAC-compliant transactions that are censored. I mean, transactions censored to be OFAC compliant. And this is the dashboard by Tony. You can check it out. This is in the last year. You can see at the builder level what are censoring and what are non-censoring in the last year. Okay, so how do you do that? How do you make it very costly for a builder to exclude a transaction from a block? There have been different proposals. You can imagine different mechanisms, different ways. The thing is, maybe you can fix this, but by fixing it, then you create other issues. So you have to be always very careful when you touch the Ethereum protocol that this is not creating other issues like DOS attacks or free data availability, we'll see. So, or strain too much the peer-to-peer network. So, there are solutions, but it's not enough to have this solution. You don't want to introduce other problems by implementing this solution. So this is a list of design criteria or design goals for anti-censorship schemes proposed by Vitalik. You should check it out, this link. Okay, then I will also tell you in advance that we have already an EIP on inclusion lists. And here I'm going a little bit through the history of when they were first proposed and go from this first proposal to the final design that is currently discussed and implemented in the EIP-7547. So let's start by talking about inclusion lists. This is a proposal to achieve censorship resistance. And more in particular, we have to talk about forward inclusion lists. So how does it work? And again, you will find details in this link. This was proposed by Francesco D'Amato. So it works this way. There is a slot, and that slot you have the proposer that has to propose the block at that slot. And in this slot, the proposer will publish an inclusion list to the peer-to-peer network. And this is only to the peer-to-peer network. The inclusion list is not going to the block. What is an inclusion list? Basically, this would be a list of transactions that the proposer decides that have to be in a block, because they're probably censored. So imagine that there is in the mempool some transactions that are in the mempool for a long time, or they are not being picked for whatever reason, or actually for no apparent reasons, so they look like they're censored. The proposer will build this inclusion list and publish it to the peer-to-peer network. Now, the builders at further slots, and this is why forward inclusion list, so the proposer is acting at slot n, the builders at slots n+1, and so on. They will build blocks with additional conditions. Okay, there is an additional condition that is forcing this inclusion list. So what are these additional rules? Either all the transactions in the inclusion list are included. So again, the inclusion list was sent to everyone in the peer-to-peer network. So everyone knows what was in the inclusion list. At further slots, the builders must put those transactions in the block, or there is only one exception for which they wouldn't do that. So if a transaction in this inclusion list is not included, it's possibly just because there was not enough remaining gas in the block. So let's say that in the slot n+1, a builder is able to fill a block completely, and there is not any more gas for the transactions in the inclusion list that was communicated to the peer-to-peer network, then it's fine. Because in this way, you can't really prove that the builder was censoring those transactions. The builder can just say, the block was full, sorry. So this was the design. And this design is solving the free data availability problem. And this is one of the rules, or anyway, guidelines that I discussed earlier from Vitalik. So how this free DA problem is solved is due to the fact that the inclusion list is never included in any block. So you cannot use the inclusion list for free data, like free call data in those transactions. We'll see it better in the next slide, but that's the main point. But there is a problem here on the fact that the inclusion list cannot be objectively enforced. So again, the inclusion list was just sent to the peer-to-peer network, but you cannot really prove that the attesters have received it. The attesters at the further block have received it. So the attesters can just pretend that they didn't see it, and they would still basically validate blocks that don't fulfill these rules because they just didn't see the inclusion list, or they can say that they didn't see it. So this was the initial design. Yeah, there is more on discussion. So the fact that you have forward inclusion lists and not just inclusion lists, this is a very nice thing. So it provides incentive compatibility because the slot n proposer, the one that publishes the inclusion list to the peer-to-peer network, can just build this inclusion list. They look at the transactions that are probably censored and put them there. And they can do that without any worry and without thinking about incentives, because they know that the value of their block in slot n will be unaffected by the inclusion list that they're building. Those transactions will be included at further slots. Then the free DA problem is solved because, as I said, the inclusion list is not posted in any block, so nobody can basically have free DA. And yeah, the problem is that inclusion list cannot be objectively enforced. So the question at this point is, how do we achieve objective enforcement without giving out free DA? We want to still have the free DA, solve the free DA problem by not posting, and that's easy by not posting the inclusion list in a block, but just sending it to the peer-to-peer network. But at the same time, we want to achieve objective enforcement. So how do we do that? And yeah, let's look more in detail at the free DA problem. What's the real problem here? And yes, this diagram, yeah, you can imagine from the style, but it's coming from Mike. And so how does it work? Let's imagine a way to have objective enforcement of the inclusion list. How would you do that? How can you basically avoid the problem that the attesters might say, I didn't see the inclusion list? Well, then you put the inclusion list in the block. You can just do that. Now, so how does it work? The proposer at slot n will commit to a transaction to be included in the list, and this transaction is valid before the execution of the block, because again, here we're talking about proposer-builder separation. But then they receive the payload from the builder, and let's say that the builder contains another transaction, this in pink, and this transaction makes the blue transaction invalid. And this is possible because the blue transaction was committed in the inclusion list before execution. So before the execution of the state, before this transaction, the blue transaction was valid. But now, after a pink transaction is executed, the blue transaction is not valid, for instance, just because the same nonce has been used by the same sender. So what happens? It happens that this blue transaction now is not valid, so it's not paying gas, but it's still included in the state. And it's still included, so it's still included in the block, it's still included in the historical state, and it's basically guaranteed that this transaction is available to the network. This means that call data here can be used as free DA for free, because you're not paying gas for this. So yeah, not nice. And this is how we arrive to a design that is very similar to what we have in the EIP. And this is a new inclusion list design. And so how does it work? Instead of putting, so at a high level, instead of putting an inclusion list in the block, we are going back to the situation in which you transmit other objects as in the peer-to-peer network. And what you send together is the block and this inclusion list that is made of a summary and of a list of transactions. So the transactions are the transactions that you want to put in the inclusion list. Basically, the transaction that you believe they're censored, so you want them to be executed at the following state. So we are still talking about forward inclusion states. There is a slot n here and a slot n plus 1. So these are the transactions, and then there is a summary, and the summary is a list of pairs of sending addresses and the gas limit. So these are the pairs, and these pairs correspond to the transactions that you have in this list of transactions. Now, how this is enforced in the slot n plus 1 or a further slot, you have an entry in the summary, so here, sender gas limit, address gas limit, is satisfied in one of three ways. A transaction from the sending address is included in the slot n payload, so here, in the same block. That's also possible, because again, we're talking about PBS, basically, because otherwise, if you're honest and you're building your block, then just put it in the block, So you don't know what's in the payload if you're the proposer, so it might very well be that transaction that you believe it's going to be censored, then will not be censored by the builder of your slot. So that's a possibility if an entry in the summary is satisfied by the same slot n. Another way is that the transaction from the sending address is included in the slot n+1 payload, so in the n+1. And the only other possible case for the block to be valid is that the transaction is not included because there was no remaining gas. So this is similar to the original design that we have seen of forward inclusion list. So if there is not enough space, then it's okay if it's not included. And this is the summary. This is slot n. This is the slot n+1. The summary first is just in the peer-to-peer object that is sent to the peer-to-peer network. But at some point, for a block to be valid, you have to include one of the summaries you have seen in the network in the slot. And basically, the entries of this summary have to be satisfied. Either because you find a transaction that is matching this entry in the previous slot or in the current slot, or there is not enough gas. So you can see the matching here. This sender A is the same sender of transaction A in the previous block. Then you have this arrow on the current block and this other arrow on the previous block. So these are the different ways this can work. And the final iteration of this design is the so-called unconditional inclusion list. Because before we have seen that a transaction can be included in the following slot, but it's still possible that there is not enough gas. So it wouldn't be included directly in the next block. But with this new design of unconditional inclusion list, you have a guaranteed execution by the end of next block. Okay? I mean at the bottom of next block. So this again slot n and slot n+1. In the slot n, you send to a peer-to-peer network the inclusion list object that is made again of the list of transactions and the summary. Actually, all of this is sent together in the peer-to-peer network in the EIP implementation. And it works similarly to what I said before, but there is no third case in which there is not enough gas, because there will always be enough gas, because basically you are adding, you have another gas limit for the transactions in the inclusion list. And it's guaranteed that they will be added to the block. So this is here you can see how the transactions are executed in time. You have the payload of slot n, and then you have the transactions coming from the slot n+1 inclusion list. They're executed in the same order you have here at the end of the block, so at the bottom of the block. And then you go on slot n+1, n+2, n+1, and so on. So how do the proposers build the inclusion list? Because this is a way for the proposers to still have some power on which the transactions are included in a block. So it's up to them, and that's how you achieve censorship resistance. You don't rely only on centralized builders, to be honest, or to avoid censorship, but you can leverage this minority, well, not necessarily, but anyway, these honest validators. How do they do that? How they build the inclusion list? They just need to run one of the default client implementations that will enable, after EIP-7547, a way to build the inclusion list. And that's quite simple in the sense that you just need to see the transactions that are in the mempool and they are not being included for no reason, because they're valid and they're paying enough fees. So the clients will automatically build this inclusion list. And of course, there is a limit because you are effectively increasing the gas limit. And the parameters we can see here. There are at most 16 transactions in an inclusion list. And at most, this is roughly 2 million gas in an inclusion list. So you can see more of the specifications on the overview here and on the actual proposal of EIP-7547. And that's all. I can't wait to see this in action. And until next time, ciao.